in order to determine the speed of a gas, we don't use one number. So a gas molecule doesn't just go collectively as one individual number in terms of a speed or velocity. The reason why that happens is that, take for example a gas, any gas. So here I'll just choose N2 gas, though it can be any gas. This N2 gas molecule is symbolized by this orange circle, is going this way in some sort of speed. This one may not go in the exact same speed inside the container because this one may be deflected. It may collide with another N2 gas molecule. It may collide with the container. It may hit something else. So all these nitrogen gas molecules, they do not have one individual speed. So we have to sort of collectively give it a speed for the whole population of N2 molecules for any type of gas molecules. And that collection of speeds, or that dispersion of diffusion rates, is called the root mean square speed. Root mean square speed is that all these thousands or millions of nitrogen gas molecules are going to go in their own individual diffusionary rates. We collectively symbolize that by one number called the root mean square speed. The symbol for speed here is u, and remember, speed is some distance over time, how fast or a rate. And the units here are the equation here is the square root of 3RT over the molecular weight. Relationship with the molecular weight. Higher the molecular weight, okay, the denominator gets very high, the whole fraction is low. Square rooting that on top of it gives you a low value of the root mean square velocity, this collective speed for all these population of gas molecules. Higher temperature means a higher value of the numerator, overall a higher value of this whole fraction, even if you square root it. So that will give you a higher root mean square speed. So the relationship is like that. The heavier gases will have a low root mean square speed. The higher temperatures will have a higher root mean square speed. The lower molecular weight gases will have a higher root mean square speed. At a lower temperature, you'll have a lower root mean square speed. So notice the relationship between temperature in Kelvin, because always we're talking about gas laws, put Kelvin as your temperature, and the relationship with the speed and the molecular weight. Another important thing about this root mean square speed equation has to do with this R. So this is not our customary R. It's an R here. That's another version. And it's 8.314 joules over a mole Kelvin. So a joule is a derived unit, and it's derived from the base unit kilogram, the base unit meter, and the base unit second. So 1 joule is actually equal to kilogram meter squared per second squared. And one final thing here, in order to get the units to cancel out, to get our final units of velocity, meters over second, the molecular weight must not be in our customary grams per mole, but it has to be in kilograms per mole. We make this adjustment in order to get the units to cancel out. So here's our equation to calculate the speed. Let's take a look and calculate the root mean square speed. Notice we're not saying speed, not like the speed of your car or the speed of a runner or the speed of a jet. We're saying the root mean square speed, again, because the diffusionary path for an individual nitrogen gas molecule will vary based upon collision frequency and based upon the diffusionary fate of an individual gas molecule. So find the root mean square speed of helium at winter and at summer. So let's first do this at winter time, where the temperature, according to this problem, is at 0 degrees C. First and foremost, let's get this into Kelvin. So that is going to be 273 Kelvin. And let's plug it into our equation 3. R is 8.314. I'm not going to use joule per mole Kelvin. Instead of joule, I'm going to substitute the derived SI unit base units. So joule, in terms of its base units, is going to be kilogram meter squared all over second squared. Okay. Temperature here is 273 Kelvin. Okay, to Kelvin. And all of that divided by the molecular weight of helium. The molecular weight of helium is 4 grams per mole. Don't get tricked here. 4 grams per mole, just as a reminder, it is 1,000 grams, gives you 1 kilogram. So we have to move the decimal point 3 places to the left, so that gives us 0.004 kilograms. So 0.004 kilograms per mole is the molecular weight. All right. So the kilogram cancel. Notice the kilograms meter square per second square came from the derived unit of the joule. Okay. Don't forget 8.314 joule over mole Kelvin. I forgot the mole Kelvin in my units here. Okay, adding the mole Kelvin here from my R back to where it is here, we should be able to see that the kilogram cancels, the mole cancel, the Kelvin cancel. I'm left with meter squared over second square. If I take the square root of that, I get meters over second. So on my calculator, that is an answer of 1305 meters over second. And that is the proper units for velocity, speed. This happens to be root mean square speed. All right, let's do this at 30 degrees C, which is 303 Kelvin. And the exact same formula we will use with the units. Our temperature is 303 Kelvin. Okay, my units of R here. The molecular weight, it's still helium, so 0.004 kilograms per mole. And doing this on my calculator and taking the square root, I'm getting an answer of 1376 meters over second. Okay, so obviously, at a higher temperature, more increased speed than at a lower temperature. Because at a higher temperature, the gases diffuse faster. So here's an application of the root mean square formula. Don't forget, when you see this equation, the units are molecular weight or kilograms per mole, and to get your units to cancel out to get meters per second, which is the final units here, the appropriate units here, we need to deconvolute the joule to what it really is, kilograms meter square over second square.